Stand at the south rim of the Grand Canyon on any morning before the crowds arrive. The light comes in low and sideways, and the canyon does something in that light that it does not do at any other time of day. The walls go red, then orange, then a deep, bruised purple in the shadows a mile below. The Colorado River catches the light like a thread of hammered copper. The scale of it hits you in the chest before your brain has time to measure it. Most people stand there and feel small. That is the natural response. That is what the canyon does to people. But there is something in that wall that almost no one looks at closely enough. Something that does not announce itself. Something that does not glow or sparkle or draw the eye the way the colors do. A line. It runs horizontally across the canyon wall. Thin, quiet, easy to miss if you do not know to look for it. Above the line, the rock layers are neat and orderly, stacked like pages in a book, each one a slightly different color, each one representing a chapter of this planet's past. Below the line, everything changes. The rock is older, darker, twisted into shapes that tell a story of enormous heat and pressure, a story of a world so different from ours that calling it Earth feels like a stretch. The line between them looks unremarkable. It is one of the most extraordinary things on the surface of this planet. Above that line, the rock is roughly 500 million years old. Below it, the rock is closer to 1.7 billion years old. That means the line you are looking at, that quiet little boundary, represents a gap of more than 1 billion years in Earth's geological record. 1 billion years of history that should be there. Layer by layer, page by page, and simply is not buried somewhere else. Not hidden. Gone. Geologists have a name for it. They call it the Great Unconformity. And the name is honest in one way and completely inadequate in another. It tells you something is missing. It does not tell you what the missing means. Here is what this story is about. That gap was not an accident. It was not a glitch in the record. Something happened to this planet. Something enormous and sustained, and in some ways still not fully understood, that consumed more than 1 billion years of Earth's own history. And the question that nobody thinks to ask when they are standing at the rim, looking down at that thin, quiet line, is not what erased it. The question is what that erasure made possible. Because 40 million years after the gap ends, the fossil record fills with something that had never existed before. Shells, skeletons, eyes, bodies complex enough to leave an impression in stone. The first animals in the full sense of the word. Earth spent 1 billion years of its own history. And what it bought with that expenditure changed everything that came after. This is the story of how pick up a rock sometime. Any rock. A piece of sandstone from a riverbank. A chunk of limestone from a road cut. A flat grey shale that splits cleanly along its layers. Hold it in your hand and understand one thing about it. You are holding a document, not a metaphor for a document. An actual document, written in minerals and pressure and time, encoding information about the world that existed when that rock was formed. The temperature of the water, the chemistry of the ocean, the creatures that were alive, the atmosphere above the surface. All of it is in there, compressed into crystal structure and chemical signature, waiting for someone with the right tools to read it. This is the fundamental insight that made geology a science. The Earth keeps records, not intentionally, not consciously, but with a fidelity that in some ways exceeds anything human beings have managed. Paper burns, hard drives fail, libraries collapse into rubble, but rock, under the right conditions, can preserve information across hundreds of millions of years with a precision that still surprises the scientists who read it. The way it works is straightforward once you see it. When sediment settles at the bottom of a body of water, it accumulates in layers. Sand, mud, the dissolved shells of dead organisms, particles carried down from eroding mountains. All of it drifting slowly down through the water column and coming to rest on the bottom in the order it arrives. The oldest material is at the bottom. The newest material is at the top. If nothing disturbs the sequence, you end up with a stack of layers that functions exactly like a stack of pages, with time running from bottom to top over millions of years. The weight of accumulating sediment compresses the layers below. Water is squeezed out. Minerals crystallize in the spaces between grains. The sediment becomes rock, and the layers become permanent. If organisms were living and dying in the water above, their hard parts, shells, bones, teeth, the mineralized remains of whatever biology had managed to construct at that point in history, get buried in the sediment and preserved. This is how fossils form. The result is what geologists call the stratigraphic record, a stack of rock layers that encodes, in sequence, the history of the environment in which they formed. Read from bottom to top. It is a chronicle. Read from the chemistry of individual layers. It is a set of measurements. Read from the fossils it contains. It is a census of what was alive at each moment in time. This record is imperfect. Sediment does not accumulate everywhere. Some environments erode rather than deposit. Some rock sequences get tilted, folded, or disrupted by the movement of tectonic plates. Some fossils dissolve before they can be preserved. The record has gaps everywhere. Small ones, the geological equivalent of a few missing sentences or a page torn out carelessly. But there is a category of gap that is different in kind from all the others. Geologists call it an unconformity. It is a surface in the rock record where there is a significant break in time, where the layers above are substantially younger than the layers below, with no record of what happened in between. An unconformity can form in two ways. Either sediment stopped being deposited for a long period, leaving no record of that time because nothing was written, or sediment was deposited and then eroded away, leaving no record because what was written was destroyed. Both produce the same thing in the rock, a surface where you can place your hand and know that somewhere between the rock above your fingers and the rock below them, time passed and left no trace. Small unconformities are common. They appear throughout the geological record all over the world, representing gaps of thousands or millions of years. They are ordinary features of a planet in motion, where coastlines advance and retreat, where mountains rise and rivers cut, and erosion claims what deposition once built. The Great Unconformity is not a small unconformity. In the Grand Canyon, where it is most dramatically visible, it represents a gap of more than 1 billion years. But what makes it genuinely remarkable is not its size in any one location. It is the fact that it appears, with variations in age and character, but unmistakable in its nature, across multiple continents. In North America, in Scotland, in Australia, in parts of China and Scandinavia. A gap that appears in one place is a local event. A gap that appears across a planet is something else. When geologists in the 19th and early 20th centuries began comparing notes across continents, when they started to realize that this particular break in the rock record was showing up everywhere they looked in the deep Precambrian, a question formed that has not been fully answered since. What could do this to a planet? Not a local flood, not a regional erosion event, not the ordinary workings of a river or a coastline. Something that operated at a scale large enough to affect multiple continents, sustained enough to last for hundreds of millions of years, and powerful enough to remove not just thin surface layers, but in some places, kilometers of rock from the face of the earth. The rock below the Great Unconformity is still there. You can touch it at the bottom of the Grand Canyon. Dark and crystalline and ancient beyond comprehension. The rock above it is still there. You can walk on it at the rim. 500 million years old, and full of the earliest complex animal fossils. What is between them is not there. And the story of what happened to it, and what that happening meant for everything that came after, is one of the most consequential stories in the 4.5 billion year history of this planet. It begins, as most great scientific stories do, not with a laboratory or a theory or a published paper, but with a man on a river who looked up at a canyon wall and felt that something was wrong. On the morning of August 13th, 1869, John Wesley Powell sat in a wooden chair mounted to the deck of a small boat called the Emma Dean and watched the walls of the Grand Canyon rise around him. He had one arm. He had lost the right one at the elbow at the Battle of Shiloh 8 years earlier. A Minié ball shattering the bones so thoroughly that the surgeons had no choice. He had gone back to the war after the amputation, commanded artillery, and then, after the war ended, he had done what some men do when they have looked at death closely enough to stop fearing it. He had turned toward the unknown. The Colorado River expedition of 1869 was, by any reasonable measure, a reckless undertaking. Powell had maps of the territory surrounding the canyon, rough and incomplete, but nothing of the canyon itself. Nobody had ever run it. Nobody knew what was inside it. The local Ute people told him there were falls in there that would swallow his boats whole. 3 of his 9 men would eventually abandon the expedition rather than continue. Hiking out over the canyon rim and into the desert above, they were killed by Paiute people 2 days later. Powell and the remaining men made it through, but that is not the part of the story that matters here. What matters is what Powell saw on the walls. He was a geologist by training, or as much of a geologist as a self-taught man who had spent years reading every scientific paper he could find could be. He understood stratigraphy. He understood that rock layers represented time and that the sequence of those layers told a story. He had read Charles Lyell. He understood deep time in the abstract. The revolutionary idea, still relatively new in 1869, that the Earth was vastly older than anyone had previously imagined, and that its history was written in its rocks. So when he looked at the canyon walls rising above the river, he was not just seeing scenery, he was reading, and what he read troubled him. The upper layers made sense. Limestone, sandstone, shale, each one sitting neatly on the one below, each one representing a chapter of sedimentary history. A shallow sea here, a river delta there, a beach, a mudflat, the ordinary accumulation of ordinary geological time. Powell could follow the sequence. He could read the story. But then, in certain sections of the canyon, the story stopped making sense. The neat horizontal layers gave way, abruptly, to something completely different. Rock that was dark and crystalline and visibly ancient. Rock that had been subjected to tremendous heat and pressure. Rock that had been twisted and folded and metamorphosed into forms that spoke of a completely different kind of geological history. And sitting directly on top of this ancient, deformed, crystalline basement, with no transition, no gradual change, no intervening layers to bridge the two worlds, were the neat, horizontal, sedimentary layers again. Two completely different kinds of rock. in direct contact, with no explanation for how they got there. Powell was not the first person to observe an unconformity. James Hutton, the Scottish geologist, had stood at a place called Sicker Point on the Scottish coast in 1788 and recognized the same kind of contact. Younger horizontal layers sitting directly on older tilted ones. Hutton had understood immediately what he was seeing, had grasped that the time represented by the gap was so enormous it made the mind reel, and had written words that became famous among geologists. He said that looking at that contact, he could find no vestige of a beginning, no prospect of an end. But what Powell was seeing in the Grand Canyon was different from Hutton's unconformity at Sicker Point. Different, not just in scale, but in character. The gap that Hutton had identified was significant. The gap that Powell was looking at, though he did not yet have the tools to measure it, was something else entirely. He wrote about it in his journal. He noted the contact between the ancient crystalline rock and the younger sedimentary layers above. He used the term unconformity, the established geological word for a break in the sequence. But the word felt insufficient, even as he wrote it. He was a precise man, a man who believed in careful observation and careful language, and he knew that the word he was using did not capture what his eyes were telling him. Something enormous had happened here, something that had erased a chapter of this canyon's history so completely that not even a fragment remained to suggest what had been written there. He did not know what it was. He did not have the isotopic dating techniques, the thermochronology, the geochronological tools that would eventually allow scientists to measure the gap precisely. He had his eyes, his geological training, and a mind disciplined enough to recognize that he was looking at a question that the science of his time could not answer. He kept floating, but the image stayed with him. In the years after the expedition, as Powell became one of the most influential scientists and government administrators in Washington, as he directed the United States Geological Survey and fought his famous, ultimately losing battle to convince Congress that the American West could not be settled on the same terms as the water-rich East. He returned to the Grand Canyon repeatedly. He mapped it. He studied it. He wrote about it at length in his 1875 report on the geology of the Uinta Mountains, where he worked through the sequence of the canyon's rock layers with the systematic thoroughness of a man trying to understand something that resisted understanding. He named the great angular unconformity he had identified. He described its character in careful geological language, and he acknowledged, with the intellectual honesty that marked his best scientific work, that the gap it represented was so large that he could not fully account for it with the mechanisms available to him. What Powell could not have known, standing in his one-armed equilibrium on the deck of the Emma Dean and looking up at that canyon wall, was that the gap he was looking at was not unique to the Grand Canyon. That the same kind of contact, the same kind of impossible jump in time, was visible in rocks on the other side of the continent, and the other side of the ocean, and on continents that no American geologist of his era had yet studied in any systematic way. He could not have known that the question he was asking in 1869 would still be generating scientific papers in the 21st century. That researchers would be using instruments he could not have imagined to measure the temperatures of individual mineral grains in rock samples and reconstruct from those measurements when the rock was buried and when it was exhumed how fast the erosion happened. He could not have known that the gap he was looking at was, in a sense that would take a century and a half to begin to understand, one of the most important boundaries in the entire history of life on this planet. He just knew something was missing. And he was right. There is a kind of scientific contribution that does not get enough recognition. It is not the contribution of the person who finds the answer. It is the contribution of the person who sees clearly enough to know that a question exists. Powell did not solve the great unconformity, but he looked at it with enough attention and enough honesty to understand that it needed solving. In the history of a mystery that would occupy geologists for more than a century and a half, that is where the story begins. Not with an answer, with a man on a river, looking up and knowing that something was wrong. In the summer of 1888, a Scottish geologist named Archibald Geikie stood on a clifftop on the northwestern coast of Scotland and looked at something that made him revise everything he thought he understood about the age of that landscape. The cliff at Knockancrag, in the Scottish Highlands, exposed a sequence of rock that seemed to violate one of the most basic rules of geology. The rule, known as the law of superposition, holds that in an undisturbed sequence of rock layers, the oldest layers are at the bottom and the youngest are at the top. It follows logically from the way sediment accumulates. If you lay down sand today and sand tomorrow, today's sand will be under tomorrow's sand. It cannot be otherwise. But at Knockancrag, ancient Precambrian rocks sat on top of younger ones. The old was above the young. The rule was broken. It took decades of bitter argument among British geologists to understand what they were actually seeing, which turned out to be a thrust fault, a place where tectonic forces had pushed an enormous sheet of older rock up and over younger rock, sliding it horizontally for miles before it came to rest in its current position. The geological structure there became famous in its own right. One of the founding examples of what geologists now call thin-skinned tectonics, but beneath the drama of that thrust fault, visible in the rocks below it, was something else. A contact, a surface where Cambrian sedimentary layers, roughly 500 million years old, sat directly on Precambrian rocks nearly a billion years older. The same kind of contact Powell had seen in the Grand Canyon, on the other side of the Atlantic Ocean, in rock sequences that had never been connected by any single geological event. The same gap, a different continent. Geologists are pattern recognition machines, by training and by inclination. When you spend years reading rock sequences, you develop an instinct for what is normal and what is not. A small gap in the record is normal. Gaps appear everywhere. They are expected. But when two geologists, on opposite sides of an ocean, working in entirely different rock sequences on entirely different continents, look at their respective canyon walls and their respective cliff tops and describe the same contact, the same break, the same impossible jump in time, a different kind of attention is required. By the early 20th century, geologists working in North America and Europe had begun to suspect that what they were looking at was not a series of local coincidences. The break in the rock record was showing up too consistently, in too many places, to be explained by local erosion or local gaps in sedimentation. Something had acted at a scale larger than any single basin, any single coastline, any single geological province. Then the work expanded to other continents. In the Kimberley region of Western Australia, some of the oldest stable continental rock on the planet, researchers found the same kind of contact, Precambrian basement rocks, in some cases nearly 2 billion years old, overlain by Cambrian or Neoproterozoic sedimentary layers, with a gap between them that dwarfed anything Hutton had described at Siccar Point. The Australian contacts were, in some cases, among the most extreme examples of the phenomenon anywhere on Earth, precisely because the Australian craton is so old and so stable that it has preserved the record of the contact almost undisturbed for hundreds of millions of years. In the Yangtze Gorges region of South China, where the Yangtze River has cut through rock sequences as old and as deeply exposed as anything in the American West, Chinese and international geologists identified the same pattern: ancient basement rocks in contact with Cambrian sedimentary layers, with a gap in between that in some locations represented close to 1 billion years of missing time in Scandinavia, in the Canadian Shield, in parts of South America. Everywhere geologists looked in the ancient cores of the continents, the stable old rock that had survived every plate tectonic rearrangement of the last 1 billion years without being fully destroyed or recycled. They found versions of the same contact. The gaps were not identical. This is an important point, and one that would become central to understanding what the Great Unconformity actually was. In some locations, the missing time amounted to a few 100 million years. In others, closer to 1 billion. In the most extreme cases, in places where the basement rock was very old and very stable, and the overlying sediment was among the youngest Precambrian or earliest Cambrian in age, the gap could be greater than 1 billion years. The contact in the Grand Canyon represents somewhere in the range of 1 billion to 1.3 billion years of missing record. Depending on exactly where in the canyon you measure and which layers you are comparing, these variations would eventually tell their own story. If the Great Unconformity were a single event, a single catastrophe that acted everywhere at once, you would expect the gap to be roughly the same age everywhere. The fact that it is not, the fact that the gap seems to be older in some places and younger in others, is itself a clue about what caused it. A clue that geologists are still working to fully interpret. But before the variations could be understood, the basic fact of the pattern had to be established. And establishing that fact across multiple continents, with the limited dating tools available in the early 20th century, was itself an enormous scientific achievement. By the middle of the 20th century, enough data had accumulated that the geological community had largely accepted what the evidence was saying. This was not a local phenomenon. This was a planetary one. Something had happened to Earth during a specific window of its history, roughly between 1.5 billion years ago and 500 million years ago, that had stripped an enormous thickness of rock from the surfaces of the ancient continents. Not everywhere equally, not all at once, but consistently enough, and extensively enough, that the record of roughly 1 billion years of Earth's history was simply absent from the geological record in most of the places where you would most expect to find it. One way to appreciate the scale of what is missing is to consider what that time period represents in the context of Earth's full history, the entire age of complex animal life, from the Cambrian explosion to the present day, spans roughly 538 million years. The gap represented by the Great Unconformity, in its largest expressions, is nearly twice that. If you compress the time that has passed since the first trilobites appeared into a single calendar year, the missing interval would represent almost 2 years. 2 years of Earth's diary, torn out. The question of what filled those 2 years, what was living and dying and evolving and being preserved in rock that no longer exists, is one that geology cannot answer. The evidence is gone, but the question of what removed it, and why, and what that removal meant for everything that followed, is one that 1.5 centuries of increasingly sophisticated science has been working to address, and the answer, it turns out, is not simple. It is not a single catastrophe, or a single mechanism, or a single moment when something decisive happened to the planet. It is a story of multiple forces, acting over hundreds of millions of years, converging on a result that none of them alone could have produced. To understand that story, you have to go back further than the gap itself. You have to go back to the world that existed before the erasure began, to a planet that looked nothing like the one we know, organized around a landmass that no longer exists, covered in forms of life, so different from anything alive today that calling them living things requires a conscious act of imagination. You have to go back to Rodinia, close your eyes, and try to picture Earth as it looked 1 billion years ago. Not the Earth of the dinosaurs, not the Earth of the first fish or the first forests. Go back further than any of that. Go back to a planet that was already 3.5 billion years old, already ancient by any measure, but still unrecognizable by ours. The first thing you would notice is the sky. It is not the blue you know. The oxygen content of the atmosphere is a fraction of what it is today, enough to support simple microbial life, but nowhere near the levels that would eventually make complex animal life possible. The sky might have had a faint orange or reddish cast in certain conditions, tinted by the chemistry of an atmosphere still in the process of becoming what it would eventually be. The second thing you would notice is the silence. No insects, no birds, no wind moving through leaves because there are no leaves, no trees, no plants of any kind on the land surface. The continents are bare rock, dark and ancient, baked by a sun that is slightly dimmer than the one in your sky today, but whose heat falls on surfaces with no vegetation to absorb it or soil to retain moisture. Rain falls and runs off immediately over bare stone and into river channels, cutting through bare stone toward a bare rocky coast. The ocean is not silent. It is full of life, in the same way a petri dish is full of life. Microscopic, invisible to the naked eye, but metabolically active and evolutionarily busy in ways that will matter enormously later. Cyanobacteria have been pumping oxygen into the atmosphere for more than 1 billion years. Single-celled eukaryotes have been experimenting with new forms of cellular organization. The boring billion, that long plateau of biological near stasis that preceded this moment, is drawing toward its close. But from the surface, from any vantage point a human observer could occupy, the world looks empty, and it is organized around a single enormous landmass. Geologists call it Rodinia, from the Russian word for homeland. It was a supercontinent, and, like all supercontinents, it was the temporary product of a process that has been running since Earth first developed. A solid crust, the slow dance of tectonic plates, driven by heat from the planet's interior, that assembles continents into giant clusters and then tears them apart again over hundreds of millions of years. Rodinia reached something close to its maximum configuration around 1 billion years ago. The exact shape is still debated, because reconstructing the positions of continents 1 billion years in the past requires working backward from evidence that is fragmentary and sometimes contradictory. But the broad picture is reasonably clear. The pieces that would eventually become North America formed the core of the supercontinent. Around that core, in configurations that different researchers reconstruct somewhat differently, were the pieces that would eventually become South America, Africa, Europe, Asia, Australia, and Antarctica, all of them pressed together into a single landmass, surrounded by a single global ocean that geologists call Mirovia. There were mountains in Rodinia. The assembly of a supercontinent is not a gentle process. When continental plates collide, the rock at their margins gets compressed and pushed upward, building mountain ranges, the way a tablecloth bunches when you push its edges together. The collision that assembled Rodinia built mountain ranges that in their time may have rivaled the modern Himalayas in height. By 1 billion years ago, those mountains were already old, already being worn down by the relentless work of rain and freeze and thaw, their peaks softening from sharp ridges to rounded summits. The interior of Rodinia was almost certainly one of the driest places on the planet. A continental interior, far from every coast, receives little moisture from the ocean. And the interior of a supercontinent, the size of Rodinia, would have been drier than any desert that currently exists on Earth. Rock, dust, and the thin biological crusts of microbial mats in the places where moisture occasionally reached. Nothing else. This was the world as it existed when the story of the Great Unconformity begins. And then, around 750 million years ago, Rodinia started to break. The mechanism of supercontinent breakup is the same mechanism that assembled it in the first place. Heat from the mantle, the slow churning of partially molten rock hundreds of miles below the surface, drives convection currents that move the plates above them. When those currents shift, they can pull a continent apart rather than pushing it together. Rifts open in the rock. Magma wells up through the cracks. The crust thins and stretches and eventually tears. And where it tears, a new ocean basin begins to form. The breakup of Rodinia was not a single event. It was a process that unfolded over tens of millions of years, with different sections of the supercontinent separating at different times and at different rates. Some pieces rifted apart relatively quickly. Others separated more slowly, grinding against each other along transform faults that generated enormous earthquakes for millions of years before the separation was complete. But the geological consequences of the breakup began almost immediately. When continental crust rifts apart, the edges of the separating pieces are uplifted. The physics of it are somewhat counterintuitive, but the result is straightforward. As the crust stretches and thins at the rift, the regions adjacent to the rift are pushed upward by the same forces that are pulling the rift apart. Rock that was previously buried at depth is brought closer to the surface. Rock that was previously at the surface is now elevated above its surroundings, more exposed to the agents of erosion and erosion. Once it begins in earnest on elevated rock, is relentless. Rain hits rock and dissolves minerals from its surface. The dissolved minerals are carried into rivers. The rivers carry them toward the coast. The fragments too large to dissolve are carried as sediment, grinding against the riverbed and each other as they go, being broken down smaller and smaller, eventually reaching the ocean as sand and silt and clay. Freeze-thaw cycles crack rock along joints and fractures, prying pieces loose that tumble downslope and enter the erosional system. Wind picks up fine particles and carries them across landscapes. This is ordinary weathering and erosion. It happens everywhere on Earth today. But when you elevate a large area of previously buried rock along a rifting continental margin, you enormously accelerate the rate at which it happens. You are presenting fresh, chemically reactive rock to the atmosphere and hydrosphere for the first time. Rock that has not been exposed to weathering before and that breaks down relatively quickly once exposed. The breakup of Rodinia. Over the tens of millions of years it took to proceed, elevated enormous quantities of rock along the margins of the separating continents and presented those rocks to the erosional forces of a planet that had been waiting, in a sense, for exactly this opportunity. The rock that was eroded did not disappear. It was transported. Rivers carried it to the coasts of the new ocean basins forming between the separating continents. It settled there as sediment, building up thick sequences of sand and mud and gravel along the continental margins. In some places, these sedimentary sequences are preserved today, and they record, in their chemistry and their character, the enormous flux of material that came off the eroding continental interiors during the Rodinian breakup. But here is the critical thing. The rock that was eroded from the continental surfaces was rock that had previously been part of the geological record. It was rock that had it not been eroded, would have contributed to the stratigraphic sequence, would have been available for geologists to read hundreds of millions of years later. Its removal was, in the most literal sense, the destruction of evidence. The first pages were being torn from the book, and this was only the beginning. The breakup of Rodinia set in motion a cascade of consequences, each following from the last. That would extend over hundreds of millions of years and reshape every system on the planet, the chemistry of the atmosphere, the temperature at the surface, the circulation of the ocean, the availability of nutrients for life. Every one of these systems was connected to every other one, and the disruption of Rodinia set them all in motion simultaneously. Among the consequences of that disruption was something that would become the most dramatic chapter in the story of the Great Unconformity, something that would take the erosion begun by the Rodinian breakup and amplify it to a scale that geology had not seen before and has not seen since. The planet was about to freeze, not in the way it had frozen during previous ice ages, not in the way it freezes today at the poles and in the high mountains, in a way so complete and so extreme that, when researchers first proposed it in the 1960s, most of their colleagues assumed they had made a mistake. They had not made a mistake. Imagine standing on the equator, not the equator as it exists today, warm and humid and biologically extravagant, the equator as it existed roughly 700 million years ago, in a world that was in the process of doing something that should have been impossible by any reasonable calculation of planetary physics. It is cold enough to freeze exposed skin in minutes. The ground beneath your feet is ice, blue-white and dense, kilometers thick in places, the product of a glaciation so extensive that it has covered not just the poles, not just the high latitudes, but has advanced all the way to the tropics and keeps advancing. The ocean to your east and west, as far as you can see, is frozen solid at the surface. Beneath the ice, the water is dark and cold and increasingly starved of the sunlight that photosynthetic life depends on. The sky above is a peculiar grey-white, reflecting the light of a sun that is slightly dimmer than the one you know, bounced back into space by the vast white surface of a planet that has become its own mirror. This is Snowball Earth, and it is not a hypothesis anymore. The evidence for it is written in rocks on every continent on the planet. The story of how scientists came to accept it is almost as remarkable as the event itself. In the 1960s, a geologist named W. Brian Harland was working on rock sequences in Svalbard, the Norwegian archipelago in the high Arctic, when he noticed something that did not make sense. The rocks contained what appeared to be glacial deposits, the characteristic mixture of unsorted sediment that glaciers leave behind when they melt. This, in itself, was not surprising. Glacial deposits are found all over the world. Records of the ice ages that have periodically cooled the planet throughout its history. What was surprising was the age of the deposits. They were Precambrian, hundreds of millions of years old. And when Harland began comparing notes with other geologists, he found that glacial deposits of similar age were turning up in places that were, at the time those deposits formed, nowhere near the poles. Paleomagnetic data, which records the orientation of Earth's magnetic field preserved in ancient rock and can be used to reconstruct where, on the planet, a rock formed relative to the poles, was suggesting that some of these ancient glacial deposits had formed at tropical latitudes, glaciers at the equator. The implication was almost too extreme to accept. For decades, the evidence accumulated without producing consensus. Various explanations were proposed to avoid the most radical interpretation. Maybe the paleomagnetic data was wrong. Maybe the glacial deposits formed through some other mechanism. Maybe the Earth's axial tilt was dramatically different 700 million years ago, redistributing heat in ways that could produce tropical glaciation without a global freeze. Then, in 1992, a geologist named Joseph Kirschvink published a short paper in which he laid out the evidence systematically, accepted its implications directly, and coined the term snowball Earth. And over the following decade, as new evidence poured in from rock sequences around the world, the scientific community gradually, and somewhat reluctantly, came to accept that the evidence was saying what it appeared to be saying. The planet had frozen, completely, or very nearly completely, more than once. The two major snowball events, called the Sturtian glaciation and the Marinoan glaciation, occurred between roughly 717 million and 635 million years ago. They were separated by a period of warming in between. But each of them appears to have involved ice coverage extending to or very near the equator, global average temperatures dropping to levels that would be lethal to most of the life currently on Earth, and a complete transformation of the planetary surface, from the diverse blue and green and brown world we know to a nearly uniform white. How such a thing could happen at all is a question that has generated an enormous amount of research. The most widely accepted answer involves a feedback loop that, once triggered, is very difficult to stop. Ice is white. White surfaces reflect sunlight rather than absorbing it. The more ice there is on Earth's surface, the more sunlight gets reflected back into space, the less heat the planet retains, and the colder it gets. As the planet gets colder, more ice forms. More ice means more reflection. More reflection means more cooling. The feedback runs in one direction and accelerates as it goes. Under normal circumstances, this feedback is checked by the carbon cycle. When temperatures drop, weathering slows, because cold rock weathers more slowly than warm rock. When weathering slows, less carbon dioxide is consumed by the weathering reactions that normally draw it out of the atmosphere. Volcanic activity continues to release carbon dioxide, regardless of the temperature. So carbon dioxide accumulates, trapping heat, eventually warming the planet back toward equilibrium. But during the period following the Rhodinian breakup, several factors conspired to push the climate toward an instability that this feedback could not stop quickly enough. The breakup of Rodinia had scattered the continental fragments across tropical and subtropical latitudes. Rock in the tropics weathers faster than rock at higher latitudes, because the combination of heat and abundant rainfall accelerates the chemical reactions that break rock down. Faster weathering drew more carbon dioxide out of the atmosphere. Atmospheric carbon dioxide dropped. The greenhouse effect weakened. The planet cooled. As it cooled, ice began to advance from the poles. As the ice advanced, the reflectivity of the planet's surface increased. The feedback loop engaged. And this time, for reasons that researchers are still working to fully understand, the normal carbon cycle correction did not happen fast enough to stop it. The ice kept coming. What happened next? Over the millions of years that the Sturtian glaciation lasted, was a transformation of the planet's surface at a scale that has no parallel in the geological record of the last 500 million years. And it is here, in the mechanics of what glaciers actually do when they advance across continental surfaces, that the connection to the great unconformity becomes most direct and most consequential. A glacier is not simply cold water in solid form. It is a machine. When a mass of ice sits on rock and is thick enough and heavy enough, its own weight causes it to flow. The ice at the base, under enormous pressure, behaves plastically. deforming and moving slowly downslope or outward from the center of the ice mass, carrying the ice above it along. This flow is slow by human standards, meters to tens of meters per year in most cases, but it is continuous. And as the base of the glacier moves across the underlying rock, it does something that no other geological agent does quite so efficiently. It grinds. Fragments of rock, incorporated into the base of the glacier, become tools, dragged across the underlying surface by the moving ice, scoring grooves into bedrock and breaking off new fragments that become new tools. The rock beneath a glacier is subjected to pressures and abrasion rates that have no equivalent in any other surface geological process short of a meteorite impact. Glaciers can erode hundreds of meters of rock from the surfaces they advance across, given enough time. During the Sturtian and Marinoan glaciations, glaciers covered enormous areas of the continental surfaces for periods lasting millions of years. The erosion they accomplished was correspondingly enormous. Rock that had been accumulating on the continental surfaces for hundreds of millions of years. Rock that encoded the geological and biological history of a planet at a crucial transition in its development, was ground down, carried to the margins of the ice, and eventually deposited in the oceans as the ice melted. This is the mechanism that made Snowball Earth the most dramatic suspect in the story of the Great Unconformity. The math is brutal in its simplicity. If a glacier erodes even 100 meters of rock from a surface, and that surface was covered by rock sequences representing hundreds of millions of years of deposition, then hundreds of millions of years of geological record disappear with it. Multiply that across the enormous areas that were glaciated during the snowball events, and you have a mechanism capable of producing exactly the kind of widespread, deeply eroded contact surface that Powell saw in the Grand Canyon and Geikie saw in Scotland, and researchers have documented on every continent for years. Through the 1990s and into the 2000s, as the evidence for Snowball Earth accumulated and the scientific community debated its details with increasing precision, the connection between Snowball Earth and the Great Unconformity seemed like it might be a straightforward answer to one of geology's oldest puzzles. Here was a mechanism. Here was a scale. Here was a time period that overlapped with the gap in the rock record. It was a compelling story. Clean, dramatic, and satisfying in the way that good scientific explanations are satisfying. But the rocks were not done talking, because when researchers began applying newer, more precise dating techniques to the Great Unconformity surfaces on different continents, and when they began comparing those dates carefully against the timing of the snowball glaciations, something complicated emerged. In some locations, the Great Unconformity contact appeared to have formed at a time that matched the snowball glaciations well. But in other locations, the data was suggesting something different. The erosion seemed to have begun earlier, not a little earlier. In some cases, significantly earlier. Earlier than the Marinoan glaciation, earlier than the Sturtian glaciation. In some cratons, the thermochronological data was pointing toward erosion events that predated Snowball Earth by hundreds of millions of years. Snowball Earth had looked like the perfect answer. But some of the rocks were telling scientists that the crime had begun long before the ice arrived. In the summer of 2022, a team of geochemists published a study in the Proceedings of the National Academy of Sciences that quietly changed the way many researchers thought about the Great Unconformity. The team had been working on rock samples from the North China Craton, one of the oldest stable pieces of continental crust on the planet. A fragment of ancient rock that has survived every tectonic reorganization of the last 2.5 billion years without being fully destroyed or recycled back into the mantle. They were using a technique called thermochronology. specifically a method that tracks the decay of uranium into helium within individual grains of a mineral called apatite. To reconstruct the thermal history of the rocks, the principle behind the technique is elegant. Helium produced by radioactive decay accumulates inside apatite grains when the grains are cool enough to retain it, below a threshold temperature of roughly 70 degrees Celsius. When the grains are hotter than that threshold, the helium escapes. So, the ratio of uranium to helium in an apatite grain is a clock that records when the grain was last at a temperature below the threshold, which in geological terms means when it was last within roughly 2 to 3 kilometers of the surface where the overlying rock had been removed by erosion. In other words, by measuring the uranium-helium ratios in apatite grains from ancient basement rocks, you can calculate when those rocks were exhumed, when the rock that once covered them was stripped away and they were brought close enough to the surface to cool below the helium retention threshold. The North China Craton data produced a result that was clear and somewhat unexpected: the exhumation signal. The moment when the basement rocks cooled as overlying material was stripped away was pointing not to the cryogenian, not to the time of the snowball glaciations, but to a much earlier period. The data was indicating major erosion of the North China Craton surface during the Paleoproterozoic and early Mesoproterozoic, in the time window associated with the assembly of the Columbia supercontinent, more than 1.5 billion years ago, before Rodinia, before Snowball Earth, before any of the events that had been the primary suspects in the Great Unconformity story. This was not entirely without precedent. Researchers working on other cratons had seen hints of early erosion events in their data, but the North China study was unusually clean and unusually explicit in its implications. And it came at a moment when enough similar data from other locations had accumulated that the pattern was becoming hard to ignore. The Great Unconformity was not one event. It was a palimpsest. A palimpsest is a manuscript that has been written on, erased, and written on again, sometimes multiple times, so that traces of earlier writing show through beneath the current text. Medieval monks used to scrape the ink from vellum pages and reuse them. And in many surviving manuscripts, scholars can see, beneath the visible text, ghostly traces of whatever was written before. The document carries multiple histories simultaneously. The basement surfaces exposed at the Great Unconformity are geological palimpsests. In some locations, the erosion that created them began during the assembly of Columbia, more than 1.5 billion years ago. Then more erosion occurred during the breakup of Rodinia, 750 million years ago. Then the snowball glaciations stripped more material away. Then warming and weathering continued the work in the intervals between glaciations, and after they ended, each episode of erosion removed more of the overlying record, and, in some cases, modified the surface that earlier erosion had created. The final result, the contact surface that Powell saw in the Grand Canyon and that appears on every continent, is not the product of any single event. It is the accumulated scar of hundreds of millions of years of intermittent but relentless erosion, each episode leaving its mark on a surface that had already been shaped by what came before. Understanding this changes how you think about the Great Unconformity in a fundamental way. If it were a single event, a single catastrophe, you would look for a single cause. A meteor impact, a supervolcano, an ice age, a tectonic upheaval, something dramatic and specific that happened at a particular time and produced a particular result. The mystery would have the structure of a crime with a single perpetrator. And solving it would mean identifying that perpetrator. But if the Great Unconformity is a palimpsest, the question changes. you are no longer looking for a single perpetrator. You are looking at a system, a planetary system in which multiple mechanisms, operating over hundreds of millions of years, each contributed to the same cumulative result. And the question becomes not who did it, but why this particular period in Earth's history was so unusually effective at erasing its own record. The answer to that question requires looking at what all the erosional episodes had in common. The assembly of Columbia involved the collision of continental fragments and the building of mountain ranges along their collision zones. High mountains erode faster than low plains because gravity pulls material downslope more aggressively, and because high elevations intercept more precipitation. The mountain ranges built during Columbia's assembly were sites of intense erosion for tens of millions of years after the collisions that built them. The breakup of Rodinia elevated rock along rifting margins, as the previous chapter described, presenting fresh material to the atmosphere and accelerating weathering and erosion across the continental surfaces adjacent to the new rift zones. The snowball glaciations deployed the most mechanically aggressive erosional force available on a planet without meteor impacts. Advancing ice sheets that ground down hundreds of meters of rock over millions of years. And between and after these major events, ordinary weathering and fluvial erosion continued, patient and unrelenting, wearing down whatever the catastrophic episodes had left behind. Each mechanism is different. Each operates on different timescales, through different processes, with different geographic distributions. But they share one thing. They are all consequences of a planet in tectonic upheaval. Columbia assembling, Rodinia assembling and then breaking apart. The climate destabilization that followed the Rodinian breakup, producing the snowball glaciations. These are not independent events. They are episodes in a continuous story of planetary reorganization, each one growing out of the geological conditions left by the previous one, each one setting the stage for the next. The great unconformity is not the scar of a single wound. It is the record of a planet going through the most dramatic tectonic and climatic reorganization of the last 2 billion years. With each phase of that reorganization, stripping more of the accumulated record from the continental surfaces and delivering it to the ocean basins. There is a phrase that forensic investigators use when they encounter a crime scene that has been contaminated, disturbed, or modified after the fact. They say the scene has been worked. The original evidence is still there, in some form, but it has been overlaid by subsequent events. And separating the original signal from the noise of later modification requires careful and patient analysis. The Great Unconformity is the most extensively worked crime scene in geological history. Every continent has been to it. Every major tectonic and climatic force available on this planet has left its mark. And the evidence of what originally happened, in what sequence and through what mechanisms, is buried beneath hundreds of millions of years of subsequent geological activity. This is why the question of what caused the Great Unconformity remains genuinely open, even after a century and a half of research. Not because the scientists working on it are insufficiently clever, but because the planet has done an extraordinarily thorough job of complicating its own evidence. What thermochronology and geochronology and isotope geochemistry are doing in the current generation of research is something like forensic archaeology, picking through a worked crime scene, layer by layer, trying to separate the signatures of different erosional episodes, trying to assign ages to different phases of the exhumation, trying to reconstruct the original surface beneath all the subsequent modification. The picture that is emerging is complex. It does not resolve to a single answer, but it has a shape that is becoming clearer. And that shape reveals something important, not just about the Great Unconformity itself, but about the nature of the period in which it formed. This was not a time when bad things happened to a stable planet. This was a time when the planet was anything but stable. When tectonic forces were reorganizing the arrangement of continents and oceans on a scale that had not occurred since the formation of the first supercontinent, when the climate was responding to those tectonic changes in ways that pushed it to extremes it had not reached in billions of years. The Great Unconformity is the geological record of a planet in transformation, a planet tearing itself apart and rebuilding itself in a new configuration, a planet whose surface, in the process of that transformation, was stripped and scoured and remade in ways that left almost nothing of what had been there before. The question of what was lost in that transformation is one that geology cannot fully answer. The evidence is gone, but the question of what was gained, what the transformation made possible that would not otherwise have been possible, is one that the rocks can speak to, because the material that was stripped from the continental surfaces did not simply cease to exist. It went somewhere. It did something. And what it did, in the oceans where it ultimately came to rest, would set in motion a chain of consequences that the planet is still living with today. Think about what happens when a mountain erodes. Not in the abstract. Literally, a mountain is rock. Rock is made of minerals. Minerals are made of elements. When rain falls on rock and runs down its surface, the water is slightly acidic, carrying dissolved carbon dioxide from the atmosphere, and that acidity reacts with the minerals in the rock. Silicate minerals break down into clay minerals and dissolved ions. Carbonate minerals dissolve directly. The products of these reactions, the clay particles too small to see with the naked eye, and the ions dissolved invisibly in the water, are carried downslope by the same rain that produced them into streams, into rivers, toward the coast. Every river on Earth is carrying a dissolved and suspended cargo of the mountains and plains upstream of it. The Amazon carries roughly 1 billion tons of sediment to the Atlantic every year. Along with an enormous chemical payload of dissolved minerals from the continent, it drains. The Ganges and Brahmaputra together carry almost as much, delivering the products of Himalayan erosion to the Bay of Bengal. The Mississippi delivers the ground-up remains of the American interior to the Gulf of Mexico. This has been happening for as long as Earth has had rivers and mountains. The ocean has been receiving the dissolved and particulate products of continental erosion for 4 billion years. But the rate at which it receives them is not constant. It depends on how much fresh rock is being exposed to weathering, which depends on how tectonically active the continents are, how many mountain ranges are being uplifted, how extensive the glaciations are, how thoroughly the surface is being stripped. During the period of the Great Unconformity, from the early stages of erosion associated with Columbia's assembly through the snowball glaciations and into the Ediacaran, the rate at which continental material was being delivered to the ocean was almost certainly far higher than it is today. The tectonic upheaval, the glaciations, the breakup of Rodinia, all of these contributed to an erosional flux of continental material that dwarfed the ordinary background rate. And that flux carried with it something that the ocean desperately needed: phosphorus. In the modern ocean, phosphorus is the nutrient that most fundamentally limits biological productivity over long time scales. It is the element that, more than any other, controls how much life the ocean can support. Every living cell requires phosphorus for its DNA, its RNA, its ATP, the universal energy currency of all cellular life. Without phosphorus, biology stops. Phosphorus enters the ocean almost entirely through continental weathering. It is locked in silicate and carbonate minerals in continental rock, and it is released when those minerals break down during weathering. The rate at which it enters the ocean is therefore directly tied to the rate of continental erosion. During the boring billion, the long plateau of biological near-stasis that preceded the Rhodinian breakup, phosphorus delivery to the ocean was low. The continents were relatively stable, the tectonic activity was relatively subdued, and the rate of continental weathering and erosion was correspondingly limited. The ocean was phosphorus-poor, and phosphorus-poor oceans support limited biological productivity. This is one of the reasons that complex multicellular life failed to establish itself during the boring billion, despite having the cellular machinery to do so. The Great Unconformity changed this. As the breakup of Rodinia accelerated erosion, as the snowball glaciations stripped continental surfaces with mechanical thoroughness, as hundreds of millions of years of continental rock was ground down and delivered to the ocean, the phosphorus locked in that rock was released into the water. The ocean chemistry changed. This is not a simple or instantaneous process. Phosphorus delivered to the ocean does not simply dissolve and become immediately available to living organisms. It interacts with iron minerals, with oxygen levels, with the physical circulation of the ocean, in ways that determine how much of it stays in the water column and how much sinks to the sediment and is removed from the biological cycle. The detailed history of ocean phosphorus cycling across the Neoproterozoic, the 500 million year period that brackets the Great Unconformity, is still an active area of research, with competing models and ongoing debates about the magnitude and timing of the changes, but the broad signal is clear in the rock record. The chemistry of Neoproterozoic and early Cambrian ocean sediments is different from the chemistry of Mesoproterozoic sediments in ways that are consistent with a significant increase in the delivery of continental weathering products. The ocean, carbon isotope ratios, sulfur isotope ratios, strontium isotope ratios in marine carbonate rocks. All of these proxies showed changes across this interval that geochemists have interpreted as evidence of a fundamental shift in the way the ocean was operating. The ocean that existed after the Great Unconformity was not the same ocean that existed before it. This matters for the story of life in a way that goes beyond the simple observation that more nutrients support more life. The specific nature of what changed, the particular chemical shifts that occurred as the products of continental erosion remade the ocean's chemistry, created conditions that had not previously existed on this planet, and that were, it turns out, precisely the conditions that certain biological experiments required to succeed. Consider calcium. Calcium is another element delivered to the ocean by continental weathering, and its concentration in seawater is directly relevant to one of the most striking features of the Cambrian fossil record. Shells and skeletons are made of calcium carbonate or calcium phosphate. Before the Cambrian, the fossil record contains almost no hard parts. After the Cambrian begins, the record is full of them. The question of why organisms suddenly began building hard structures at the Cambrian boundary is one of the most debated questions in evolutionary biology. And the answers proposed involve everything from changes in predation pressure to changes in genetic regulatory systems. But among the factors that researchers consider is the availability of the raw materials from which hard structures are built. An ocean with more calcium in it, delivered by a period of intense continental erosion, is an ocean in which the energetic cost of building a calcium carbonate shell is lower. The thermodynamics favor calcification more strongly. Organisms experimenting with hard structures face a lower chemical barrier to making that experiment work. This is not a sufficient explanation for the Cambrian explosion. The causes of that event are multiple and complex, and still debated, and no single factor, including ocean chemistry, can account for it fully. But ocean chemistry is part of the story. And the ocean chemistry of the late Neoproterozoic and early Cambrian was shaped, at least in part, by the enormous erosional episode that the Great Unconformity records. The rock was not simply lost. It was transformed into ocean chemistry. It became the medium in which the next chapter of life's history was written. There is another dimension to this transformation that is less about chemistry and more about geography. As the continents that had been assembled into Rodinia broke apart and drifted into new configurations, and as sea levels rose and fell in response to the glaciations and deglaciations of the Cryogenian, the geography of the shallow ocean changed dramatically. Shallow ocean environments. The continental shelves, where sunlight penetrates to the seafloor and nutrients from the continents are most concentrated, are the most biologically productive parts of the ocean. They are where most marine life lives, where most marine fossils form, where the biological record of the ocean is most richly preserved. The breakup of Rodinia created new coastlines, new continental margins, new shallow ocean environments where none had existed before. The flooding of continental interiors during the warm intervals between and after the snowball glaciations created vast, shallow seas over areas that had previously been dry land. This geographic expansion of shallow marine habitat, combined with the chemical enrichment of the ocean by continental erosion, created something that had not existed during the Boring Billion. A large, chemically rich, spatially extensive shallow ocean environment, full of nutrients and flooded with sunlight, in which organisms with new capabilities and new body plans could expand and diversify. The stage was being set, but the actors who would perform on that stage had their own story, one that ran parallel to the geological story through all the upheaval of the Neoproterozoic, one that is written not in continental rock, but in the genes of every living thing on Earth today. Before we can understand what appeared after the gap, we have to understand what existed before it. What was alive during the billion years that the erasure consumed? What was lost? And what managed to survive? And how the survivors were shaped by everything the planet put them through. Because the Great Unconformity did not only erase geological history, it erased biological history too. There is a question that geology cannot answer, not because the science is insufficiently advanced, not because the researchers working on it lack the tools or the intelligence or the dedication, but because the evidence required to answer it was physically destroyed, ground to powder by glaciers and dissolved by rain and carried into ocean basins where it was buried under kilometers of subsequent sediment and in many cases pulled back into the mantle by subduction, returned to the interior of the planet from which it originally came. The question is this: what was alive during the billion years that the Great Unconformity consumed? We know the broad answer: microbial life, single-celled organisms. The eukaryotic cell, already invented by the time the Rhodinian breakup began, experimenting with new forms of organization in an ocean that was, as the previous chapter described, chemically limited in ways that constrained how far those experiments could go. The Boring Billion, that long plateau of biological near stasis, had been running for hundreds of millions of years before the tectonic upheaval of the Neoproterozoic began. And its biological character, a world dominated by microbial mats and single-celled eukaryotes, was still largely in place when the first phases of the Great Unconformity erosion started. But the broad answer is not the full answer, and the full answer is the one we cannot have. Think about what a billion years means in biological time. The entirety of vertebrate evolution, from the first fish with a backbone to every bird and mammal and reptile and amphibian alive today, fits inside roughly 500 million years. The colonization of land by plants, the development of forests, the evolution of insects and amphibians and reptiles, and then mammals. The entire story of life, as most people understand it, unfolded in a time span shorter than the gap in the Grand Canyon wall. In 1 billion years, evolution can do an enormous amount, even working with the relatively simple cellular toolkit of the Proterozoic, even constrained by the nutrient-poor and oxygen-limited ocean of the boring billion. 1 billion years of selection and mutation and genetic recombination is a vast canvas. The organisms alive at the beginning of that billion years and the organisms alive at the end of it, assuming continuous evolution throughout, would be separated by more generations and more accumulated genetic change than separates a bacterium from a blue whale in the modern world. What happened in all those generations? What experiments did evolution run in the organisms living through the Rhodinian supercontinent, in the oceans of a world before the cryogenian glaciations, in the biological communities of a planet that looked nothing like the one we know? What body plans were tried and abandoned? What metabolic innovations were developed and then lost? What forms of multicellular organization appeared and disappeared, leaving no descendants and no fossils, preserved in rock sequences that no longer exist? We do not know. We cannot know. The rock that would have told us was the rock that was removed. This is the specific and irreversible nature of what the great unconformity represents as a biological event. It is not just a gap in the geological record. It is a gap in the biological record. A gap produced not by the failure of life to exist or to leave traces, but by the physical destruction of the medium in which those traces were preserved. There is a philosophical distinction here that is worth sitting with. A fossil is not life. It is the record of life, the impression or mineralized remnant of an organism that once existed, preserved by the specific conditions of burial and chemistry that allow organic material to survive long enough to be replaced by mineral matter. The existence of a fossil requires not only that an organism lived and died, but that it lived and died in an environment where preservation was possible, that its remains were buried quickly enough to avoid decomposition, that the chemistry of the burial environment was right for mineralization, and that the rock containing the fossil survived for hundreds of millions of years without being eroded, subducted, or metamorphosed into a form where the fossil is no longer recognizable. All of these conditions have to be met simultaneously. The failure of any one of them produces the same result: no fossil, no record, no evidence. During the interval of the great unconformity, in the rock sequences that no longer exist, all of those conditions may have been met in countless locations. Organisms may have lived and died in shallow marine environments and been buried in sediment and mineralized into fossils and preserved in rock that accumulated layer by layer over hundreds of millions of years. The record may have been there, complete and detailed, encoding the biological history of a planet at a crucial transition in its development. And then the glaciers came, or the continental margins were uplifted, or the rivers cut down through the sedimentary sequences and carried them grain by grain to the coast. And the fossils that may have been there, the record that may have existed, was destroyed as thoroughly and as irreversibly as if it had never formed. What we are left with are hints, molecular clocks, the technique of using the rate of mutation in DNA to estimate when different lineages diverged from their common ancestors, can in principle reach back into the Proterozoic and tell us something about when different groups of organisms were separating from each other evolutionarily. These analyses consistently suggest that the major lineages of eukaryotic life, the ancestors of plants, animals, and fungi, were already diverging from each other during the Proterozoic, during the billion years that the Great Unconformity consumed. The molecular evidence implies a biological diversification that the fossil record, for the obvious reason, cannot confirm. Chemical signatures in ancient sedimentary rocks, the organic molecules called biomarkers that can survive for hundreds of millions of years, even after the organisms that produced them are long gone, provide another window. Some biomarkers specific to particular groups of eukaryotes have been found in Proterozoic rocks, suggesting that certain lineages were present and active even in the absence of a body fossil record to confirm it. And in the few locations where Proterozoic rock sequences survived the Great Unconformity erosion, where conditions were right for preservation and the rock was stable enough to avoid being stripped, there are fossils, acritarchs, the organic walled microfossils of uncertain biological affinity that are found throughout the Proterozoic record. Stromatolites, the layered structures built by microbial mats that have been present in the geological record since nearly the beginning of life on Earth, and in some late Proterozoic sequences, more complex forms, simple multicellular structures, and the enigmatic tubes and ribbons that suggest organisms experimenting with organization beyond the single cell. But these survivals are the exception. They are the fragments that escaped the erasure, the pages that were not torn out, the portions of the record that happened to be in locations where the conditions for survival were met and the conditions for destruction were not. They give us a fragmentary glimpse of a biological world that was almost certainly far richer and more complex than the glimpse suggests. The richness and complexity that we cannot see is the real loss. There is a concept in information theory called the counterfactual. It refers to what would have happened under different circumstances. The path not taken. The event that did not occur. Counterfactuals cannot be observed. By definition, they represent what is absent rather than what is present. But they can sometimes be inferred. And the inference of a counterfactual can tell you something important about the nature of the situation you are actually in. The counterfactual of the Great Unconformity is the billion years of biological history that would exist in the rock record if the erosion had not occurred. The organisms that would be named and described in textbooks. The evolutionary transitions that would be documented in detail rather than inferred from molecular clocks. The body plans that appeared and disappeared without leaving any trace we can read. We know this counterfactual existed. We know, with reasonable confidence, that during the billion years of the Great Unconformity, life was present, active, and evolving. We know that the organisms of that time were the ancestors of everything that came after, that every living thing on Earth today traces its lineage through the biological community of the Proterozoic, through the organisms whose records are missing. They were our ancestors, and we have almost nothing of their story. This is what makes the Great Unconformity something more than a geological curiosity. It is a reminder of the fundamental fragility of the record on which all historical science depends. History, whether human or geological or biological, exists only insofar as it leaves traces, and traces can be destroyed, not misplaced, not hidden, physically, irreversibly destroyed, returned to the raw materials from which they were made, leaving nothing but absence. The Grand Canyon wall shows you that absence, that thin, quiet line between the ancient crystalline basement and the younger sedimentary layers above it, is the boundary of a silence so complete that no instrument will ever penetrate it fully. Below the line, there is rock that remembers being deep in the earth. Above the line, there is rock that remembers shallow Cambrian seas. Between them, there is nothing, not emptiness, nothing, a billion years of a living, changing, biologically active planet compressed into the thickness of a geological contact surface that you could cover with your hand. But here is what the silence does not mean. It does not mean that the billion years was wasted. It does not mean that the life that existed during that time, the organisms that lived and evolved and died in the missing rock sequences, were without consequence for what came after. The biological lineages that survived the Neoproterozoic upheaval, the eukaryotic cells that had been refined by hundreds of millions of years of selection in a challenging ocean, the genetic innovations that had accumulated through the long, slow work of the boring billion and the subsequent tectonic disruption, all of this was carried forward in the organisms that made it through. Evolution does not require a complete fossil record to do its work. It requires only living organisms, héritable variation, and selection pressure. All three were present throughout the Proterozoic, throughout the billion years of the great unconformity, in organisms whose names we do not know and whose forms we cannot see. The survivors of that billion years, the lineages that made it through the snowball glaciations and the chemical upheaval and the tectonic reorganization and all the other pressures that the Neoproterozoic brought, emerged into the Ediacaran period, carrying a biological inheritance that we can only partially read. Genes that had been shaped by hundreds of millions of years of selection. Cellular mechanisms that had been refined by challenges we cannot document. Evolutionary experiments in multicellular organization that may have been running for far longer than the fossil record reveals. What those survivors did with that inheritance in the ocean that the great unconformity had helped to reshape is the next chapter of the story. And that chapter, unlike the one before it, is written in rock that still exists, in fossils that have survived, in a biological record that, for the first time in a very long time, begins to speak clearly. 600 million years ago, give or take the uncertainty that attaches to any date that old, a thin layer of sediment settled onto the floor of a shallow ocean, somewhere in what is now South Australia. Nothing about the settling was unusual. Sediment had been settling onto ocean floors for 4 billion years. The process is as ordinary as gravity, as continuous as the weathering of rock on the continents above. Fine particles drifting down through the water column, accumulating in layers, recording in their chemistry the conditions of the water above them. What was unusual was what some of those particles carried with them as they settled. Impressions, not rock impressions, not mineral crystals, the shapes of living things, pressed into the soft sediment before it hardened, preserved with a fidelity that captured not just the outline, but in some cases the internal structure, the quilted texture of the surface, the pattern of growth that the organism had followed during its life. The organisms that made those impressions were unlike anything in the modern world. They were flat. Some of them, oval or frond-shaped or organized into radially symmetric patterns that suggest a body plan with no clear front or back. No head, no identifiable sensory organs. They were soft, leaving impressions rather than the mineralized remains that later organisms would leave. They ranged in size from a few centimeters to nearly 1.5 meters for the largest known examples. They had no hard parts that we can identify. They left no mouth parts, no eyes, no limbs, no structures that correspond to anything in the body plans of modern animals. They were the Ediacaran biota, named for the Ediacara Hills of South Australia, where they were first systematically described, though they have since been found on every continent, in rock sequences spanning roughly 80 million years, from about 575 million to 538 million years ago, and they represent something that had never appeared in the fossil record before. Organisms large enough to see with the naked eye. The significance of this is easy to understate and important to grasp fully. For the previous 3.5 billion years of life on Earth, the fossil record is dominated by microscopic organisms. Stromatolites are visible structures, but they are built by colonies of microbes rather than by individual multicellular organisms. The acritarchs and other single-celled eukaryotes of the Proterozoic are microscopic. The entire boring billion, that long plateau of biological near stasis, is a world of the invisibly small. The Ediacaran organisms are the first things in the history of life on this planet that a human being standing in those ancient shallow seas could have seen with unaided eyes, could have reached down and touched, could have recognized, even without any biological training, as living things rather than just surfaces and textures. Something had changed. What had changed was the product of everything the previous chapters of this story have described. The Rhodinian breakup, the snowball glaciations, the chemical transformation of the ocean, the expansion of shallow marine habitat, the biological inheritance carried by the surviving lineages through hundreds of millions of years of Proterozoic upheaval, all of it converging in the Ediacaran period on conditions that made visible macroscopic, multicellular life, not just possible, but apparently explosively successful. The Ediacaran biota appeared and diversified over roughly 80 million years, which, in geological terms, is a relatively short interval, but in biological terms is long enough for considerable evolutionary experimentation. Different body plans, different growth strategies, different apparent ecological roles. Some of the Ediacaran organisms may have been photosynthetic, hosting symbiotic algae in their tissues the way modern corals do. Some may have absorbed nutrients directly from the sediment surface they rested on. Some may have been suspension feeders, drawing organic particles from the water above them. What most of them appear not to have had is a predator large enough to eat them. The Ediacaran world was, as best we can reconstruct it, a world without significant predation at the macroscopic scale. The Ediacaran organisms lived on the seafloor in what researchers sometimes describe as a garden, a world of largely sessile, largely defenseless organisms spreading across shallow sediment surfaces without the evolutionary pressure to develop armor or speed or elaborate sensory systems to detect and evade enemies. This was about to change in a way that would transform the history of life on Earth more dramatically than any event since the origin of the eukaryotic cell. The boundary between the Ediacaran period and the Cambrian period, dated to roughly 538 million years ago, is one of the most studied and most debated boundaries in all of geology. Not because it is dramatic in the rock record, though some sections show abrupt changes at this level, but because of what it represents biologically, just below the boundary. In Ediacaran rock sequences, the fossil record shows the soft-bodied, largely symmetric, relatively simple organisms described above, at and above the boundary. In the earliest Cambrian rock sequences, the record begins to show something different. Trace fossils, the tracks and burrows and trails left by organisms moving through or over sediment, appear in new forms and new abundance. Small, shelly fossils, the mineralized fragments of the first organisms to build hard external structures, begin to appear. And then, over the first 20 million years of the Cambrian, in what geologists consider a geologically instantaneous interval, even though it spans a time frame longer than all of recorded human history times 2000. The full diversity of animal body plans that has characterized complex life ever since appears in the fossil record. Eyes, limbs, guts, muscles, nervous systems complex enough to coordinate rapid movement, exoskeletons of calcium carbonate or calcium phosphate, JAVs, gills, the fundamental architectural innovations of the animal body, most of which are still present in every animal alive today, appear in the rock record within this narrow window. The Cambrian explosion. It is worth being precise about what the Cambrian explosion was and was not, because imprecision about it leads to misunderstanding both its significance and its causes. It was not the origin of life. Life had existed for more than 3 billion years before the Cambrian explosion. It was not even the origin of complex multicellular life. The Ediacaran biota demonstrates that complex multicellular organisms preceded the Cambrian by tens of millions of years. It was not an instantaneous event. 20 million years is brief by geological standards, but it is not sudden in any meaningful biological sense. What the Cambrian explosion was, specifically, was the relatively rapid appearance in the fossil record of animals with hard parts, the mineralized shells and skeletons that preserve so much more readily than soft tissue, combined with a diversification of animal body plans that established the major groups of animals that have been present on Earth ever since. Most of the major animal phyla alive today, from arthropods to mollusks to echinoderms to chordates, the group that eventually produced vertebrates and ultimately us, have their first clear fossil representatives in Cambrian rock. The causes of the Cambrian explosion are genuinely complex and genuinely debated. No single factor accounts for it. The answer is multiple and interactive. A set of biological and environmental changes that reinforced each other in ways that made the diversification self-accelerating once it began. But the environmental context in which the Cambrian explosion occurred is part of that answer. And that context was shaped by everything the great unconformity represents: the ocean chemistry. The phosphorus and calcium, enriched by hundreds of millions of years of continental erosion delivered by the processes that created the great unconformity. The expanded shallow marine habitats created by the fragmentation of Rodinia and the flooding of continental margins, the oxygen levels in the ocean and atmosphere, rising in the aftermath of the snowball glaciations as biological productivity recovered and organic carbon was buried in the newly expanding marine sedimentary environments. These are the conditions in which the Cambrian explosion occurred. Not the sufficient causes of it, but the necessary conditions, the environmental context without which the biological experiments of the Cambrian, even with the genetic and cellular innovations that the Ediacaran organisms had developed, might not have succeeded in the particular way they did. And those conditions were, in significant part, the product of the same tectonic and climatic upheaval that stripped 1 billion years of rock from the continental surfaces and created the great unconformity. The trilobite, arguably the most iconic organism of the Cambrian, and one of the most successful animal body plans in the history of life, spending nearly 300 million years on Earth before going extinct at the end of the Permian, was a product of this world. Its mineralized exoskeleton of calcite, its compound eyes with their individual calcite lenses, its segmented body plan with its appendages adapted for walking, swimming, and in some species, filter feeding. All of this was built from the biochemical and evolutionary raw materials that the Cambrian Ocean provided. The calcium for its skeleton came, ultimately, from the weathering of continental rock. The oxygen for its metabolism was produced by photosynthetic organisms thriving in an ocean enriched by continental nutrients. The shallow marine habitat it lived in was shaped by the same tectonic forces that had been reorganizing the planet's geography for hundreds of millions of years. Draw the line of cause and effect from Powell's unconformity at the bottom of the Grand Canyon to the trilobite preserved in the Cambrian limestone at the top, and you trace a path through the breakup of a supercontinent, the freezing of an ocean, the chemical transformation of a sea, the expansion of a shallow marine world, and the biological experiments of organisms whose fossils we cannot read because the rock that contained them no longer exists. The missing pages did not disappear into nothing. They dissolved into the ocean. They became the chemistry of a sea that had never existed before in the history of this planet. They became the medium in which the first animals built their shells and swam their first strokes and opened their first eyes on a world that the billion years of their hidden ancestry had helped to make. The torn chapter did not end the story. It became the opening lines of the next one. In 1986, a geologist named Nicholas Christie Blick was working on a rock sequence in the Panamint Range of Death Valley, California, tracing the character of the Great Unconformity contact across a series of outcrops exposed by the basin and range faulting that had stretched the crust of the American Southwest into its current geography of alternating mountain ranges and desert valleys. At one point, during the fieldwork, he placed his hand flat against the contact surface. The crystalline basement rock below his fingers was roughly 1.7 billion years old. The Cambrian sedimentary rock above his fingers was roughly 530 million years old. The gap between those two ages is 1,170 million years, more than a billion years of Earth's history. Between his palm and the rock face, it was pressed against. He noted it in his field book and moved on. There was more outcrop to measure, more samples to collect, more data to gather. The gap was not new to him. He had spent years working on Proterozoic geology and understood what the contact represented as well as anyone working in the field at the time. The hand against the rock was not a dramatic gesture. It was the ordinary physical interaction of a scientist with the material he studies. But the gap did not become smaller because it was ordinary. 1,170 million years. Take all of recorded human history. Every name we know, and every event we can date, and every building, and every text, and every piece of music, and every scientific discovery, and every political revolution, and stack it end to end. It amounts to roughly 5,000 years. The gap between Christie Blick's palm and the rock face behind it contained more than 200,000 complete spans of recorded human history. And in all of that time, we have almost nothing. This is the situation that geology faces when it confronts the Great Unconformity. And it is worth being completely honest about what that situation means. It means that there are questions about this planet's history that will never be answered. Not eventually. Not with better technology. Not with more funding, or more researchers, or more sophisticated instruments. Never. Because the evidence required to answer them was physically destroyed and is not recoverable. Science does not like to say never. The history of science is full of problems that seemed permanently intractable and then yielded to new approaches and new theoretical frameworks. Thermochronology has opened windows into the thermal history of rock that previous generations of geologists could not have imagined. Molecular clocks allow researchers to push evolutionary timelines back into periods where the fossil record is silent. Geochemical proxies in ancient carbonate rocks are reconstructing ocean chemistry from intervals where no direct biological record survives. These tools have genuinely advanced the understanding of the Great Unconformity. The timing of erosional episodes on different cratons is better constrained than it was 20 years ago. The ocean chemistry changes across the Neoproterozoic are more precisely documented. The picture is sharper, and it continues to sharpen with each new study. But sharper is not complete. And for the Great Unconformity, complete may not be achievable, because the record says what the record says. What the record does not say may be silence, or it may be the echo of a destruction that left no direct trace. This is not a technological problem. It is a thermodynamic one, a rock that has been ground to powder by a glacier, carried by a river to the coast, deposited as marine sediment, compressed, and then pulled back into the mantle by subduction, is not a rock that any instrument will ever read again. The information it contained is gone in a way that is final. The atoms that made it up still exist, somewhere in the mantle, or recycled into new rock through volcanism. But the specific arrangement of those atoms that encoded the geological and biological history of a particular place at a particular time is destroyed. The questions this destruction leaves unanswerable go to the heart of how we understand the history of life on this planet. Molecular clock analyses consistently suggest that many major animal groups diverged from each other deep in the Proterozoic during the interval of the Great Unconformity, long before they appear in the fossil record. The discrepancy between the fossil record and the molecular clock is one of the most persistent problems in evolutionary biology. The Great Unconformity offers a partial explanation for that discrepancy. If the rock sequences that would have contained the early fossil record of these animal groups were removed by the erosional processes that created the unconformity, then the absence of early animal fossils from the Proterozoic record is not evidence that early animals did not exist. It is evidence that if they did exist, the record of their existence was destroyed. Absence of evidence is not evidence of absence, and nowhere is that distinction more literally true than here. The missing rock is not a negative result, it is a destroyed result. The experiment was run, the data was collected, and then the data was ground to powder by glaciers and returned to the ocean. Every science that works backward from present evidence to past events faces the same fundamental constraint. The past does not survive intact. It survives in fragments, in the portions of its record that happen to meet the conditions required for preservation, that happen to be in locations where destruction did not reach. What we know about the past is always a sample of what existed, filtered through the accidents of preservation and discovery. The Great Unconformity makes this constraint unusually visible because the destruction was so extensive and so well documented. You can stand at the Grand Canyon wall and point to exactly where the destruction occurred. You can measure its magnitude. You can trace its effects across multiple continents, but the same principle applies, at smaller scales and with less dramatic visibility, to every other part of the geological and biological record. Everywhere you look, in deep time, you are looking at a sample, a fragment, the portion of the past that happened to survive. What that means for the questions we can ask, and the confidence with which we can answer them, is something that the best scientists working on deep time history hold in mind as a constant check on overinterpretation. The Great Unconformity is the largest and most clearly visible example of that incompleteness in the entire geological record of this planet. It is the place where Earth's history most honestly shows you its own limits, and those limits are not a flaw in the record. They are a feature of a planet that is alive, a planet that moves and changes and destroys and rebuilds, that has never stopped doing to itself what it did during the Neo-Proterozoic upheaval. The geological record of this planet is not a library carefully organized and preserved against loss. It is the output of a system that creates and destroys simultaneously, that builds rock sequences and erodes them, that assembles continents and tears them apart, that supports life for billions of years and periodically subjects that life to conditions that test it to its limits. The Great Unconformity is that system showing you its work. The 1 billion years it consumed are gone. The questions they would have answered are unanswerable. The organisms that lived during them are known to us only through the molecular signatures they left in the genomes of their descendants and the rare fossils that survived in the portions of the record that were not destroyed. But the gap they left behind is not empty. It is full of what happened next. And what happened next is the reason you are here to read about it. Go back to the South Rim. The same morning. The same low light coming in from the east, catching the upper walls of the canyon before the shadows below have lifted. The same crowds beginning to gather at the viewpoints. The same cameras raised. The same sharp intake of breath from people seeing it for the first time. Find the line. You know where to look now. Not at the colors. Not at the depth. Not at the river, a mile below, catching the early light. Look for the boundary between the dark, twisted, crystalline rock in the lower canyon walls and the neat horizontal sedimentary layers above them. Look for the place where one world ends and another begins, separated by a contact surface so thin that you could cover it with a playing card. You are looking at 1 billion years of Earth's history, compressed into the thickness of a geological contact. But you are looking at it differently now. When most people see the Grand Canyon for the first time, they see depth. They see the accumulated thickness of geological time laid out in horizontal strata, each layer a chapter, each color a different environment. The whole sequence, a record of the patient accumulation of history across hundreds of millions of years. They see a place where time is visible, where deep time becomes tangible in a way that no other landscape on Earth quite manages. That response is correct, but it is incomplete, because the most important feature of the Grand Canyon is not what is there. It is what is not there. The missing billion years. The chapters that should exist between the crystalline basement and the Cambrian sedimentary layers. The record of a world in transformation whose evidence was consumed by the transformation itself. Everything you have followed through this story leads to this line. The breakup of Rodinia, the ancient supercontinent that existed before any of the landscapes we know, elevating rock along its rifting margins and beginning the long process of continental erosion that would run for hundreds of millions of years. The snowball glaciations. The ice advancing from the poles all the way to the equator, grinding continental surfaces with a mechanical thoroughness that no other geological process except a meteor impact can match. The ocean chemistry changing as the products of that erosion. The phosphorus and calcium and silica and iron that had been locked in continental rock for hundreds of millions of years, dissolved and entered the sea. The expanded shallow marine habitats created by the fragmentation of a supercontinent into smaller pieces with longer coastlines and wider continental shelves. The biological survivors of all of that upheaval. The eukaryotic lineages that had been refined by hundreds of millions of years of selection in a challenging ocean, emerging into a world whose chemistry had been remade by the very processes that destroyed the record of their ancestry. The trilobite that lived in the Cambrian Sea above this line and died and was buried in the sediment that eventually became the limestone you can touch at the canyon rim, was made from the ocean that the great Unconformity helped to create. The calcium in its exoskeleton was delivered by the weathering of continental rock during the tectonic upheaval of the Neo-Proterozoic. The oxygen its metabolism required was produced by photosynthetic organisms thriving in an ocean enriched by continental nutrients. The shallow sea it lived in was the product of a planetary geography reorganized by the same forces that stripped a billion years of rock from the continental surfaces. The line you are looking at is not a boundary between presence and absence. It is a boundary between two different kinds of presence. Below it, the presence of an ancient and largely silent world. Microbial and microscopic and slow, running its patient experiments across hundreds of millions of years in an ocean that was not yet ready to support what would eventually emerge from it. Above it, the presence of a world transformed, a world of shells and eyes and movement and predation and the restless biological experimentation that has been running ever since. Between them, the gap, the record of the transformation itself, a billion years of upheaval, consumed in the process of producing the world that came after it. This is what it means to say that Earth did not lose a billion years. It spent them, not intentionally, not with any awareness of what the spending would produce. A planet does not intend anything. It follows physics. The same physics it has always followed. The convection of its mantle, the movement of its plates, the response of its climate to the changing arrangement of land and sea, and the slowly brightening output of its star. The spending was not a choice. It was a consequence. But consequences can be as consequential as choices. The billion years that the great unconformity consumed were not wasted time. They were the investment that the Cambrian world required. The erosion that stripped the continental surfaces delivered the nutrients that enriched the ocean. The tectonic reorganization that elevated rock into the path of erosion also created the shallow marine environments where complex life would eventually flourish. The snowball glaciations that destroyed rock sequences also destabilized a biological and chemical equilibrium that had been holding complex life in check for hundreds of millions of years. Destruction and creation, running simultaneously, each inseparable from the other. There is something in this that goes beyond geology, something that the rocks are telling you, not about Earth's history specifically, but about the nature of transformation in systems too large and too complex to plan their own futures. Every major transition in the history of life on this planet has been preceded by a period of disruption. The oxygenation of the atmosphere, catastrophic for the anaerobic life that had dominated for 2 billion years, created the conditions for every aerobic organism that has ever lived. The Permian extinction, which killed more than 90% of all species on Earth, cleared the ecological space that the dinosaurs and eventually the mammals would fill. The asteroid that ended the non-avian dinosaurs was a catastrophe by any measure, and also the event that made the age of mammals possible. The Great Unconformity fits this pattern. The disruption was enormous. The loss was real and irreversible. A billion years of geological and biological history gone, and out of that loss, a world emerged that would not have been possible without it. This is not a comfortable thought if you sit with it long enough. It does not resolve into a simple lesson about silver linings or the necessity of suffering or the hidden purpose of destruction. The billion years was not destroyed for a reason. It was destroyed by physics. The biological record it contained was not sacrificed to produce the Cambrian world. It was collateral damage in a planetary reorganization that had no awareness of what it was doing to the organisms caught up in it. But the result is what it is. The ocean that the erosion enriched, the shallow seas that the tectonic fragmentation created, the biological survivors that the upheaval tested and filtered and ultimately released into a remade world. The trilobite, with its calcite eyes, looking out on a Cambrian sea from a body built of elements that had traveled through hundreds of millions of years of geological transformation to reach it. That trilobite is downstream of the Great Unconformity in the most literal sense possible. So is every animal that came after it. So are you. Reading these words, in a brain built of calcium that was once continental rock, and oxygen that was once the product of ancient photosynthesis, and carbon that has cycled through the atmosphere and the ocean and the bodies of organisms across 4 billion years of the planet's history. You are downstream of the Great Unconformity. You are the long consequence of a billion years of planetary spending. And you are the first thing in the history of this planet that is capable of standing at the edge of the gap and understanding what the gap is. Powell stood at the same edge, on the same river, looking at the same canyon walls. In 1869, he saw that something was missing. He did not have the tools to understand what the missing meant, or how large it was, or what had caused it, or what relationship it had to the world he was living in. He just saw the contact, felt its wrongness, and wrote it down. The century and a half of science that followed his journey down the Colorado River has not resolved every question about the great unconformity. It has made the picture sharper and the gap more precisely measured and some of the mechanisms better understood. But the gap itself remains, as large and as irreducible and as honestly present as it was when Powell first saw it. You cannot fill 1 billion years. You can only understand what the filling would have required, and what the emptiness eventually made possible. Stand at the rim long enough, in the low morning light, before the crowds get thick and the noise makes reflection difficult. Look for the line. Find the boundary between the dark ancient basement and the younger sedimentary layers above it. Place your hand against it if you can reach it. Below your hand is a world that was already ancient when the Cambrian began. Above your hand is the world that the Cambrian built. The world of shells and eyes and bodies. The world that eventually, across 500 million years of subsequent evolution, produced the nervous system and the curiosity and the capacity for wonder that brought you to this canyon wall in the first place. Between your hand and the rock face is the gap, 1 billion years of Earth's history, gone, in the sense that matters most. Present. In every consequence that followed from its going, you are standing at the largest missing chapter in Earth's memory, and you are what happened after it.